So I think we can start now. And before we start, please we all mute yourself, except of course except Jason and Jason. We will record the seminar. Are you okay with it?
Yes.
Yes,
No problem. Yeah.
And after your talk, we will plot your slide and also the video on the website so that the people can see it again.
Sure.
Okay, and so it is my pleasure today to introduce our speaker of this week, Chen. He is a professor at Mathematics Department of National Taiwan Normal University. He received his PhD degree from University of Washington in Seattle in 2004 under the supervision of Professor Chen. His research area is mainly in continuous optimization with side interest in non-smooth analysis and operation research. His publication include around 125 journal papers and one book published by Springer. Now, Jason, please.
Okay, thank you. Thank you means for your introduction. Hi, I'm Jason Chen from Taipei, Taiwan. So right now it's in afternoon. I think in Australia is also afternoon, right? Evening. Okay, so it's good to see all of you here in such a very special way. And also it's my pleasure to give a talk at this seminar. And today I'm going to talk about a very simple equation, which is called absolute value equations. So let's see, okay, how can I make this on? Okay, so the absolute value equation is in this form, ax plus b times absolute value of x equals b. Where A and B are n by n matrices. And of course, absolute value of x means the component-wise absolute value of the vector x. And when B equals negative identity matrix, then this equation just reduces to a special form like the equation 2, which is also called AVE. Okay, so you see the AVE is a very simple equation. So let's talk about a little bit about the history of the AVEs. So actually this equation was first introduced by Long in 2004. Actually, originally it just appears in this theory, which is kind of alternative theorem. It says this absolute value equation has a unique solution, or another equation as a non-trivial solution. Sorry, and Maksarian already proved that Savian AVE is NP hard in 2006, and also Prokofiev also shown that checking whether the AVE has unique solution or multiple solutions is NP complete. Okay, and I just mentioned that the AVE was originally introduced in 2004 in this alternative theory, but at that time, Norm did not use the name absolute value equation. And this name actually was termed by Magnasarian in 2006. And since then, there have been many studies on these equations by many researchers. Okay, and also especially Mangasarian and Meyer and Prokofiev, they both proved that this equation is actually equivalent to LCP, which stands for linear complementarity problem. But the form of LCPs proven by Mangasarian and Prokofiev are different, a bit different. So since the equivalence between AVE and LCP, so we know that AVE is NP hard. So it's another way to see solving AVE is NP hard. Okay. So why do we study the AVE? Okay, so because many mathematical programming problems like linear programs, quadratic programs, biometric games, and even mixed integer programs, they all can be recast as an LCP, which means linear complementarity problems. And we just saw that LCP is equivalent to AVE. And of course, we see that the AVE is quite simple, right? The equation. And in my opinion, the most important thing is the AVE is an equations. So it attracts more audience for solving equations, okay? About the solvabilities, okay? So as I mentioned earlier, Mangasarian and Meyer, they show that AVE is equivalent to the standard LCP if the eigenvalue of eigenvalues of A does not contain 1. So if 1 is not an eigenvalue of A, then the AVE, the absolute value equation is equivalent to the standard linear complementarity problem. And Prokofiev further improved this result by showing that actually he can take out the assumptions on A and B. So without any assumptions on A and B, so the AVE is equivalent to another LCP, which is not the standard LCP. So the dimension of this LCP is bigger than the standard LCP that Mangasarian proves. Okay, so in general, so if solvable, so the AVE could have either unique solution or even multiple solutions. So for example, exponentially many solutions, okay? So that's about the solvabilities of the AVE. And there have already some numerical ways or some numerical algorithms for solving the AVEs. So for example, the successive linearization algorithm or the generalized Newton algorithm, and even the generalized Newton algorithm with semi-smooth and smoothing steps, okay? And another popular one is smoothing type algorithm, okay? So they have been proposed for solving the AVEs, okay? And also they have some variants or kind of extensions of the AVE, absolute value equation. The first one is called AVP. Is an abbreviation of absolute value programs, which means it contains absolute value of variables in the objective functions and constraints, okay? And the second extension or variant is the absolute value equation associated with the second order cone. So just denoted by SOCAVE, okay. And the third one is associated with the circular cone and denoted by CCAVE. I just point out that for these two variants or extensions, the absolute value of X is defined in a different way, okay. So more specifically, so the absolute value of X is not a component-wise of vector of X. It's defined by the square root of X dot X. And here dot is a very special or certain Jordan product. So that's the difference between SOC AVE, CC AVE, and the traditional AVE. Okay, and it is possible that the AVE has no solution. Okay, here Prokofiev already proved under these conditions, so the AVE has no solutions. Okay, and it's in reality or in practical models, so it's possible. So they also provide some reasons why it caused the infeasibility of the AVE. Okay, and in this case, when AVE is infeasible, has no solution, so there's a way to do the correction of infeasible AVEs, which is studied by these researchers already. Okay. And today I will present two approaches for solving AVEs. Because we know that at the beginning of my talk, we already saw that the AVE is indeed equivalent to an complementarity problem, especially LCP, right? So many approaches or algorithms are based on this reformulation. And another approach is just rewrite or reformulate the AVE as a system of non-smooth equations. Okay, and today the first approach I want to show is I just rewrite it as a system of smooth equations. So instead of non-smooth equations, so I rewrite it as a system of smooth equations, and then just apply the traditional smoothing type of algorithm to solve the equations. And the second approach is a neural network approach, which is just an ODE model. Okay, so let's move on to the first approach. The main idea is quite simple. So we define the mapping capital HI here. So it's a mapping from R to the n+1 to R to the n+1. So the first component, mu, is a parameter. Okay, and the rest components are ax plus b times smoothing function capital Phi minus b. So just recall that our absolute value function, absolute value equation is ax plus b times absolute value of x minus b. So here we are trying to use kind of smoothing function to replace or to approximate the absolute value function. Okay, so the main idea is when capital HI is 0, then if and only if the x will be a solution to the AVE. Okay, so that's the main idea of the first approach. So it's quite simple. Okay. Here I just show you 4 smoothing functions we employed in this smoothing idea. So remember here we have capital Phi, which is composed of small Phi, and each Phi actually is a smoothing function to approximate the absolute value function, real value absolute value function. Okay, so here are 4 examples which are smoothing functions to approximate the absolute value function. So especially I just show you that Phi4, the last one, is constructed in a different way. I will show you later. And theoretically, it's very easy to show that each Phi is just continuous differentiable, and of course, it's a smoothing functions to approximate the absolute value function. So which means when mu goes to 0, so each Phi mu t just approaches to the absolute value function. So that's why we call them smoothing functions. Okay, So here is the picture for first smoothing function phi1. So we will see that when the parameters mu goes from 0.5, 0.3, 0.1, and 0.01, so their corresponding graphs just getting closer to the absolute value function, right? So you can see actually is a smoothing function. And for the second function phi2, so again, so when mu goes from 0.5, 0.3, 0.1, and even to 0.01, so it's getting closer and closer to the absolute value function. Okay. And phi3, okay, phi3, so it's similarly behavior. Okay. And phi4, so I just mentioned earlier, so this function is constructed differently. Okay, why is different? Okay, so you can check the parameters. Okay, when mu goes from 0.5, 0.3, 0.1, 0.01, so you see, so it's kind of buttoned up. Okay, so the graph going up, so going from bottom to up and getting closer to the absolute value function. So that's the behavior of phi4, which is different from those three functions, phi1, phi2, and phi3. Okay, it's a routine work to check. Okay, so capital Phi is just continuous differentiable with computable Jacobian. Okay, okay. So if we put all these four functions together, so what will you see? Okay, so you will see. So actually, the red line, which represents phi2. So phi2 seems is the closest function which best approximates the absolute value function, right? Phi2. Okay, we just saw phi2 is the function which is closest to the absolute value function. Okay. And actually from this figure, okay, so we see phi2 is the function which best approximates the absolute value function, and also we observe this local behavior among all these functions. Okay, so phi3 is above of phi1 and above of phi2 and above of absolute value function, and phi4 is below the absolute value functions. Okay, so we see three functions, phi1, phi2, phi3 are above the absolute value function, and phi4 is below the absolute value function. And actually there's a local behavior, and it could be even proved theoretically. Okay, so it's from the graph we recognize this behavior geometrically, and actually algebraically we can also verify it by defining the distance of two functions in the infinity norm. Okay, so using the infinity norm, we can compute the infinity norm of phi1 and absolute value of t is just this amount, which means the distance of phi1 to absolute value function is 2 ln2 times mu, and the distance of phi2 to the absolute value function is mu over 4, and the distance of phi3 to absolute value function is just 2 mu. Okay, and then how about phi4? So the distance of phi4 to absolute value of t is mu over 2. Okay, so you can sum up all the distances. We just compute. Okay, so we have inequalities like this one. And this just verify that phi2 actually is closest to absolute value function, because the distance of phi2 to absolute value function of t is the smallest one. Okay, and just recall that. Okay, so we have a local behavior like this one, and we just verify that phi2 is the function which is closest to the absolute value function. Okay, okay. So theoretically and geometrically, we prove that. So phi2 is the function which best approximates the absolute value function. Then we will ask, how about numerically side? Okay, does phi2 perform best among all these four functions in some algorithm, or especially in this talk, the smoothing type algorithm? Okay. Okay, so before I show you the numerical result, we need to have only one assumption. Okay, so this assumption is already used to guarantee that the Jacobian of capital HI is invertible, which means the AVE has unique solution. So we can check it when we do the coding. Okay, so otherwise we are not so sure the solution is a real solution. Okay, so we just put this assumption. Okay, and then we use the very traditional smoothing type algorithm. So we set up the initial data, stopping criteria, so update for directions, and we also have updates for step size. Okay, so it's already there for a long time. So the smoothing type algorithm. Okay, and then it's not hard to prove that. So under this assumption, so the algorithm is well defined. Okay, and the generated sequence has a accumulation point, which is a solution to the AVE. Okay, so it's just routine check. So anyway, I will show you our numerical results. Okay, okay. So the first test example or problem is actually an ODE. Okay, so you see why it's an ODE. So after discretization, the ODE is indeed a very special AVE. Okay, even by this one. So after discretization, so it becomes an AVE. So that's why we use this one as a test. Actually, is suggested by one reviewer. Okay, so here's the problems or dimensions we test, and we also use a very special performance profile to present or to tell you which method, which functions is better. So in general, it's kind of hard to compare different type of algorithms or different approaches. So because their stopping criteria could be different. Okay, so the concept of performance profile was proposed in 2002 by some I don't remember his name, by one guy from MIT. Okay, so you can view performance profile like this way. So the vertical line is kind of probability. So how many percent of the problems, of the test problems, could be solved successfully under the restriction? Okay, so originally, if we set our restriction is very high, so maybe 90% of the problems can be solved by this approach or by this function. Okay, and then another 50% could be solved by the phi4. Okay, and so on. And when the conditions is relaxed, so the restrictions is getting relaxed, then in most cases, so all the problems can be solved. Okay, so in other words, you can view or interpret the performance profile in this way. So if the curve is higher, then its corresponding algorithm or its corresponding approach is better than the others. So that's the very simple interpretation of performance profile. Okay, so you will see in terms of iteration numbers, so the curve of phi2 is higher than the other curves. So which means so the algorithm based on phi2 performs better than the others. Okay. Okay. So how about CPU time? So for CPU time, we also see that the curve of phi2 is higher than the others, which means phi2 actually the smoothing algorithm working along with phi2 performs better than the other functions. Okay, and phi1 is the worst one. Okay, so this from no matter from CPU time or iterations. Okay, and the second test province is a randomly generated province. Okay, so to ensure the solutions exist, so which means we have unique solution, we need to set up some commands, okay, to ensure the assumption is held and even the solution is the solution exists. Okay, and we also test a few problems. Okay, so here's represents the dimensions. Okay, so again, so from the iterations and CPU time, you will see phi2 is the best one. Actually, the best choice to work along with the smoothing type algorithm. And in this case, phi1 or phi3, okay, is the worst one. Okay, so in summary, so actually we have two test problems. One is for AVE1, okay, another one is simple form in AVE. So from iteration aspect, phi2 always performs better than the others. Okay, and I just record you that here's the local behavior we have for these four functions. Okay, so we just saw that phi2 is the function which best approximates the absolute value function, and numerically it also performs better than the others. Okay, from iterations and also from CPU time. Okay, but this phenomena is not always guaranteed. Okay, just keep in your mind that it is not always guaranteed. But for our algorithm and our smoothing functions, phi2 is the function best approximates the absolute value function, and also performs best. Okay. So this is just a couple remarks. phi2 is the best choice of smoothing function to work with the smoothing type algorithm from our numerical experiments. Okay, and I also want to mention that piecewise functions seems better than the others. Actually, phi1 and phi3 are quite popular in engineering community. Okay, but phi1 and phi3 actually perform not well in this type of algorithm. Okay, so it's very interesting to check whether such phenomena occurs in other type of algorithm. Okay, so that's why we keep going to study another approach, which is the neural network approach. Okay, so in our first approach, we show that we use 4 smoothing functions, and for this continuing work, we just want to try to study all possible ways to construct smoothing functions. Okay, and actually, the way to construct smoothing functions were already there. Okay, so long time ago, mathematicians already proved something there. So we just look for them from the literature. Okay, so the first way is the convex conjugate way. Okay, so if we are given a function f, okay, so the convex conjugate of f star is defined by this one, right? Okay, and then using this formula, okay, so which means we take the conjugate of g, the conjugate of the sum of two functions. One is g. G actually is the conjugate of f, okay, and then take another d function, which is the proximity function satisfying one strongly convex condition, okay. Then the mathematicians tells us that we can get smoothing functions from this formula. Okay, it's good. Okay, so let's see. Okay, so here is just a definition of one strongly convex condition. Okay, or in general, mu strongly convex condition. So because we need to take a very special function d here in this formula, okay, and sum up with g and then take the convex conjugate, then we can get the smoothing function f mu, okay. So the first example is, okay, so because we are trying to construct smoothing functions for absolute value of x, okay, so we rewrite absolute value of x in this way, okay, and then take the function equals g squared over 2, okay, and following the convex conjugate way, okay, so that's the first function, the first smoothing function we can get, which is the traditional Hubble function, okay. So Hubble function is also popular in engineering community, okay, and it's also possible to just rewrite the absolute value of x in another form, okay, like this one, and then take another d function, okay, then we'll get the second smoothing function, phi2, okay. And another possible choice of d function is this one. So then we will get the third smoothing function, okay. So just quickly review these three functions, okay, by convex conjugate smoothing way, okay. So the first way, by convex conjugate smoothing way, so we can obtain three smoothing functions, phi1, which is the Hubble functions, and phi2 and phi3, okay. So that's by convex conjugate way, okay. And the second way is the monoproximal smoothing way. So it's already exists long time ago, okay. So monoproximal approximation says that using this formula, okay, so we can get smoothing functions, okay. And I think probably some of you already know that the smoothing functions constructed from monoproximal way is always convex, continuous, finite value, and differentiable, right? Okay. And especially if we use a monoproximal smoothing way to construct smoothing functions, so we get Hubble function again, okay? So which means Hubble functions can be constructed by monoproximal way as well, okay? So that's the second way. And the third way is the Nestodorf smoothing way, okay? So Nestodorf considers a very special case of non-smooth convex functions in form of this one, okay? And then he suggests that by using this formula, so we can get smoothing approximation. So to be honest, I don't quite understand why Nesterov consider this very special format. Okay, so anyway, so using this this formula, so we can get smoothing functions. So in this case, if you want to construct a smoothing function by Nesterov formula, okay, so we need to put absolute value of x into the very special form. Okay, so which means we have a, b, and q, okay, and then take a d function again. So just very surprisingly, so get Hoover function again. Okay, so remember the Hoover function phi1 can be obtained from the first way, convex conjugate way, the second way, a Monroe proximal way, and even Nesterov smoothing way. Okay, and the fourth way is the infimum convolution. Okay, so that's the definition of infimum convolution of two functions f and g. Okay, so we take the infimum convolution of f and g. Okay, and then using this formula, we can get smoothing approximations of f. Okay, so by taking the infimum convolution of f, original function f, and another function omega mu. Okay, so an example by infimum convolution is if you take the absolute value function, because we want to construct smoothing function for absolute value function. So we plug in f by absolute value function, and then take the infimum convolution with this function to another omega mu, which is the piece power of the norm function. Okay, then we kind of obtain a family of Hoover functions. Okay, so which is called Hoover function of order p. Okay, so given by this formula. Okay, so especially when p equals 2, it just goes back to the Hoover functions. But in general, we have different value of p. Then you have different type of Hoover function, which is called Hoover function of order p. Look at the pictures of Hoover functions of order p. Okay, so you can see when p gets closer to 1, then the Hoover function of order p is getting closer to the absolute value of x. Okay, so that's the examples for smoothing functions obtained or constructed by infimum convolution. Okay. A good news is actually the infimum convolutions already covers the previous 3 ways, which means the convex conjugate Monroe proximal Nesterov ways are very special cases of infimum convolution. So for example, if you take omega mu as these functions, and omega mu as the square of norm of mu, and even omega mu is the conjugate of d, then we will verify that convex conjugate smoothing way, Monroe proximal smoothing way, and even Nesterov smoothing ways, they are all special cases of infimum convolution. So in that case, so infimum convolution just unify all the previous ways. Okay, just keep that in your mind. Infimum convolution is very important. Okay, And the final way, okay, the fifth way is the traditional convolution smoothing way. Okay, so I think this already appear in many references or in the literature. You will see this is a popular way to construct smoothing function. So basically, we just follow 3 steps to construct smoothing functions by this convolution. So the first one, the first step is just choose kernel function d of x. Okay, so kernel function means d of x is always non-negative, and the integral of d of x equals 1. Okay, and then use kernel function to define s head. Okay, and then use s head to define p head. So this p head function will be smoothing functions to approximate the plus function. Okay, so for example, I can show you 4 smoothing functions obtained by choosing these 4 kernel functions. Okay, so we have 4 smoothing functions to approximate plus function, not absolute value function yet, by choosing these 4 kernel functions. Okay, and then use this fact. The absolute value function is sum of plus function and minus function. Okay, and then we can construct smoothing function to approximate absolute value function. Okay, so then just applying these 4 kernel functions, we will obtain 4 smoothing functions. Okay, 4, phi 4, phi 5, phi 6, and phi 1 again, Fourier function again. Okay, so Fourier functions can be obtained in each way. Okay, so using the kernel functions, I show you here these 4 kernel functions. So we can obtain another 4 smoothing functions. One of them is Fourier function again. Okay, and if we take a very special EP kernel function, okay, then we get a piecewise smoothing function. Okay, so this is phi 7. Okay, and this kernel function is also popular, Gaussian kernel function. Okay, then in that case we get a very weird, very strange. It's weird smoothing function because we have a very special formula here. Okay, so this is the S smoothing function. Okay, to sum up, the 8 smoothing functions we have. Okay, phi 1, phi 2, phi 3, phi 4. Okay, 5, 6, 7, and 8. So from all previous infimum convolutions and traditional convolutions. Okay, so we get these 8 smoothing functions. Okay, to approximate the absolute value function. Okay, so put all the graph together. Okay. Okay, just take a look. We'll see 3 functions. Okay, 3 functions are below the absolute value function, and all the other 5 are above the absolute value function. Okay, and theoretically, we can also prove this local behavior. Okay, so these 3 functions, phi 1, phi 2, phi 3, okay, below absolute value function, and 4, 5, 6, 7, 8 are above. Okay, and we'll see phi 1 and phi 5 is kind of closest to absolute value function than the others. Okay, then we'll see. Do phi 1 and phi 5 perform better than other smoothing functions. Okay, so I will show you our numerical result. So just recall in the first reformulation, we define capital HI, okay, by this one. And if we further consider a minimization problem by taking square of norm of capital HI, okay, then we can construct an ODE model, okay, like this one. So the right hand side of the ODE model is just the gradient mapping of psi. Psi is the square of norm of capital HI, okay. So it's kind of a very standard construction ODE model, which means neural network approach, okay. And it's a routine work to check. This one will provide solution to the AVE, okay, especially the equilibrium point of the neural network ODE model will be the solution to the AVE under this condition, okay. Okay, and especially because the ODE models we care about the solution trajectory. So now the CPU time, now the iterations. So for this ODE approach, so usually we care about the solution trajectory. Okay, so it's very standard way to prove that the equilibrium point of the neural network is not only asymptotically stable, but also exponentially stable. Okay. And so because that's the neural network model, so ODE model, so we care about the solution trajectory. So which means it's very important to estimate the error, okay, the error of solution to the real solution, okay. So the first example we test is it's a very simple AVE, okay. So here's the matrix A and B, okay. So we use all 8 smoothing functions, okay. And because we just look at so eventually, so the solution trajectory, we are very close to the real solution. So I just show you the convergence behavior from the view of error term, okay. And actually, you will see 3, 4, 3, 5, and 7 perform better than the other smoothing functions, okay. So because the error term drop down very quickly, okay. Second example is a complementarity problem, LCP. So in this case, just rewrite it as a AVE again. So we test it, and we also see that 3, 4, 3, 5, 3, 7 perform better than the other smoothing functions. Okay, and this one is again a LCP. So similarly, we have 3, 4, 5, 6, 7. Okay. Okay, and that one is a randomly generated example again. Okay, so we just put some commands to ensure the solution exists. Okay. Okay, so in this case, so it's also seen that 3, 4, 5, 6, 7, okay, performs better than the others. So if you want to record the local behavior, sorry, I just show you quickly. So in this local behavior, we just say phi1, phi5 are functions closer to absolute value function, but phi1 does not perform well in this neural network approach. Phi5 does perform well, but phi1 does not. Okay, so that's why I said the phenomena is not always guaranteed. So in general, we observe that these 4 smoothing functions, 3, 4, 3, 5, 6, 7, perform better than the others, working along with the neural network approach. And especially these 4 functions are constructed from convolution weight. Okay, so which means the other ways, convex conjugate way, monoproximal way, next total way, and even in Feynman convolution, they don't produce good smoothing function working along with neural network approach. Okay, so I think this is a very interesting discovery. Okay, so of course I believe it deserves further investigation. Okay, and lastly, I just also want to point out that if we are given 2 smoothing functions and do the convex combination, okay, so we take phi1, phi2 as smoothing functions, and then take and then do the convex combinations. Okay, so it's again a smoothing function for observed value of x. Okay, so in this case, for example, you can take Fourier function from those 3 functions below the observed value function, and phi2 functions from the pool of those functions above the observed value functions, and then take convex combinations. And you can even try different value of t, right? So in that case, we can obtain many more smoothing functions. And how about their performance? Okay, so I think it's also another future study. So I think that's my talk for today. Thank you for your listening. Thank you.
Thank you, Jason, for the very nice talk. And I see in the chat, Janos have a question. Janos, can you ask a question to Jason now?
Yes, you have shown some numerical results on slides 36 and 37. And so my question is, I mean, every one of these functions can be applied with several different values of mu. And the question is, like, how do you compare that? If you, for example, one of the smoothing functions might be very good for one parameter and very bad for another. So I don't understand how this can be compared.
The comparison, the first approach, the comparison is based on the concept of performance profile. Okay, so in my first approach, I mentioned that the performance profile is a concept proposed by one guy from MIT in 2002. Okay, so it's hard to explain this in very detail, but in general, if you are given 100 problems, so you can see if the first approach or first algorithm or first function can solve the problems 90% or 80%, then it will present, represented in this curve.
But how do you choose the set of problems?
Okay, the set of problems, yes, the set of problems for our approach. So I just show 2 problems. So actually, this is an ODE problem, and after discretization, so it becomes an AVE, right? And then we can test it in different dimensions. Okay, and the second one is randomly generated test problems. Okay, and we also set commands to ensure the solution exists. So that's the first approach. Okay, but the second approach, so for your question, the second approach is the neural network approach. So basically it's a ODE model. So the performance profile does not apply here. So we just show you the the comparison by the arrow term. So you will see the functions produce nice arrow term. Okay, so that's the way we do comparisons for the second approach. Okay.
Yeah, but what I don't understand is really, I mean, yeah, for one mu, one of these approaches might be very good on certain test problems. For another mu, they might be very bad. And how do you capture that?
Oh yes, I think your question is very interesting. Yeah, mu is okay. You can also compare different type of view. So, but for our comparison, so we just, okay, for example, we use the same mu and then compare different functions, but it's still possible to decide which mu is better than for each function. And then you can use the best one to compare. It's another possible way to do comparison in this way. Yeah, right.
Yeah,
right.
yes,
then
yes.
I understand.
Okay, so that question is from Evgeny Novinsky. Can you add directly to Jason? Hello?
So you need to open up microphone.
No.
Okay.
The question.
In the past, Evgeny had problems with microphone. You better read his questions.
Okay.
Okay.
So the question is a convergence exponential in time in numerical ODE experiments?
Pardon?
Is a convergence exponential in time in numerical ODE experiments? It's about the speed of convergence.
Yes. Yeah. Okay. So the speed. So for the second approach is kind of is a ODE model, right? So the convergence rate is represented by stability. So exponentially stability. Okay, sorry. Basically, I think so. For the second approach, so stability of neural network means the convergence rate of ODE model. So exponentially stable is quite good. So in the ODE community, and for the first one, first approach, so we have a convergence rate. It's kind of Q, not Q superlinear. I show you somewhere. Sorry. Okay, so here is the convergence rate. Okay, it's not as good as so like quadratic Q, quadratic.
Yeah.
So okay. Anyway, so here's the convergence rate. Okay.
Okay. So next questions. Anyone has a question for Jason? So I have one questions. I think your function phi2 in the first part and phi5 in the second part is the same, right? As the same.
Mm-hmm.
And it look very similar to the Muro envelope. Is that, and so we can obtain the function phi by that takes the Muro envelope.
Yes, yeah, Muro, yeah, Muro envelope. If you use Muro envelope way, okay, actually you get the Hooper function. I think I put where
yes, but
yes.
We can obtain the function phi5 or no?
Phi5 V5 is from convolution, not from model envelope. Okay. Yeah, V5 is not.
Okay.
Yeah, okay. So from model envelope, you get V1. Okay.
I only get V1. Okay. But V1 is quite good, but not the best, right? Okay.
No. Here V1 is not good.
Okay. So did you try with the Muro envelope, but you replace the Euclid distance by Bresman distance?
Oh.
Then you have a Bresman Muro envelope. It's also can give you smoothing function.
Sorry, I didn't know this.
So
yeah.
So in the Muro envelope, you replace the Euclid distance, the norm square, by another distance, Bresman distance, for example.
Oh, okay, I see. Yeah. Okay. Yeah, good. I think it's good to try. Yes.
Yeah, it might be good. I don't know.
Okay.
Okay. Any suggestion or comment? Here so Evgeny Newminsky have another question. You need second order optimality condition for stability, which mean exponential convergence. Is the case for all smoothing functions?
Oh, okay, I see. Yeah, the stability is as long as okay, sorry. So as long as the condition is satisfied here, yeah, that's fine for our test smoothing functions. So the equilibrium point converges in exponentially stable way.
So it's true for all the smoothing function you have, right?
Yes.
Okay, thank you.
Thank you.
Any other questions?
Okay, maybe I want to ask Professor Chen. Yeah, I mean, is there any theoretical guarantee? I mean, to show that like phi2 is superior than others, sort of. I mean, theory for that.
So in first approach.
Yeah.
Okay, so that's a very good point actually. So we were trying very hard to find theoretical evidence to support why phi2 performs better than the others, and so far we couldn't. So sorry, but it's very good to do this way. Yeah, so we always want to find theoretical evidence, but so far we couldn't reach it. Yeah, it's very important. Yeah, thank you.
Yeah, and also, I mean, it has been mentioned that it's not easy to compare the performance using performance profile. I mean, certainly that's not easy because you have to collect all kinds of problems there with different parameters. So that means, yeah, it's not easy to compare numerically. But I understand. So what you did is, in fact, you have different dimensions and many different problems. So in this way, numerically, it is I mean, it can be people can be convinced that I mean, someone is good or some is not so good. But if there are some theoretical proof, then it will be a better, I mean, to understand somehow. Yeah.
Yes. I agree. Yeah, I agree.
Yeah. It's very great. I mean, I understand it's very hard, in fact, to find theoretical stuff. But anyway, yeah, your presentation is very good, very interesting functions you found. Yes.
Actually, recently in some other algorithm we are working out, we just find a very small clue, you know, just small evidence that's we can show it. But in general, for these two algorithms, we so far we cannot prove anything theoretically to support our observations.
But it probably doesn't matter. I mean, in practical problems, people can use just choose one. It works well. Then that's it. Probably the engineers don't care about proof. That's what I'm thinking. So,
yeah, it's very important. I think eventually we still need to theoretical evidence. Yes. Yeah.
Okay. All right.
Thank you.
Okay. Thankful, Seth. Any other comment or questions? If we don't have any other comment or questions, let's thank the speaker again. Thank you, Jason, so much for giving the very nice talk in our webinar. And
thank you.
Yes, and hope you keep your interest with our seminar series.
Okay, thank you.
Thank you so much. And
so all of you are welcome to visit Taipei. Okay, just feel free to let me know. Okay.